All right, so in the previous chemistry lecture video, we gave an introduction to chemistry, but more than that, we learned how to name organic compounds. So we talked about things known as.
Okay? See you if okay? Bye. Bye bye.
So we, in our last lecture, we said we have things known as elements. You can have elements on the periodic table, and different types of elements combine together to make substances called compounds. So we
Compounds.
say that an element is a substance in its purest form that cannot be changed or split by any physical or chemical means. And if two or more compounds come together, chemically together, they make something known as a compound. And for compounds, we have got two types of compounds that we said. We have got ionic compounds and we have got covalent compounds. Then we learned how to name covalent compounds, and we also learned how to name ionic compounds. With covalent compounds, we say that we have got certain, we start with with the metal first, then we name the non-metal, oh sorry, for covalent compounds, we said we give the name of the first element and then we use prefixes to indicate the number of atoms in the second element. For example, if we had something like CO3, then we say this is the first element, which is sulfur. Then we say this is the second element, which is oxygen, but we won't name it as oxygen, so we're going to say oxide, but we also consider this, the subscript there, which is 3 meaning tri. So this would be sulfur trioxide. So we get the root name of oxygen and we end it in IDE. So for covalent compounds, this is how we name. We use prefixes, which you have to remember. Like mono means one, di means two, tri means three, um, tetra means four, penta means five, etc. So we use these prefixes to name these covalent compounds. However, with ionic compounds, we say that we name the metal first. So the first thing that you're supposed to name is the metal, because an ionic compound comes from the attraction between a metal and a non-metal. So you name the metal first, then you name the non-metal, making sure that the non-metal again ends with IDE. But again, the prefixes with these ionic compounds don't necessarily mean tri, di, etc. They actually mean charges on ions. For example, if we have maybe ion with a charge 3 and we have sulfate with a 2 minus ion, what we're going to see here is that for us to name this compound here, we have to have a net charge. So remember, I told you in the previous lecture video that all ionic compounds and all covalent compounds, they are electrically neutral. They are electrically neutral. But for covalent compounds, for them to be electrically neutral, the number of positive charge has to be equal to the number of negative charge. So remember, chemistry has to make sense, or rather science has to make sense uh, for you to really enjoy the topic or the subject itself. So most of teachers would say, all right, so if you have an ionic compound like this, you have got ion 3 plus and a sulfate there, what you're supposed to do is sort of cross multiply, and it would be Fe2SO43. I don't like such methods of cross multiplying because this doesn't make sense. Like, why are you exchanging the charges? It doesn't make sense explaining it that way. So for it to make sense in terms of ionic compounds, no wonder I said in terms of ionic compounds, we don't use these mono, di, etc. because the numbers, when we're talking about ionic compounds, you know, ionic compounds meaning a bond between a metal and a non-metal. So this is a metal and a non-metal. We don't talk about things like mono, di, tri. The numbers at the bottom do not mean there are three oxygen atoms. No, the numbers mean the charge. So the charges are the ones that we consider. So here, the net charge is +3, and here the net charge is -2. So for us to have an equal amount of charge, we'll need to add one more ion 3 plus there, and two more of these, SO4 2 negative, SO4 2 negative, such that the total charge here will be +6, and 2, 4, 6. The total charge on the other side will be -6, meaning for these two elements to form a properly balanced ionic compound, we're going to need two ion 3 pluses. So we're going to need two ion 3 pluses like this. Then we're going to need 1, 2, 3 sulfurs, SO4, 3. You even put it in brackets there to show that this 3 indicates that there are 3 of these sulfate ions. So my SO4, the SO4s, there are 3. And then this 2 here shows that there are actually 2 of these there, so that we can make the charge balance up, +6 there and -6 there. So I won't just say, all right, Fe 3 plus SO4 2 minus, then you cross multiply, then your formula will become Fe2 SO4 open brackets 3. It does work, yes, but what I want you to understand is why are we cross multiplying? Let me just explain this once more. So I have an ionic compound, and let's say I want to write down the formula of iron sulfate. And iron sulfate is an ionic compound because it's made between a metal and a non-metal. So there is an electrostatic attraction between the anions and the cations. And the formula, we have an ion Fe3 plus and SO4 2 minus. What you can do is cross multiply. You change the ions there. This 2 here is going to go towards ion. We'll say Fe2. And then this 3 here is going to go towards the entire sulfate. So we'll say open brackets SO4. Then we'll add these 3 outside. But this method works, but where is the explanation? So here's the explanation. I said ionic compounds are electrically neutral. The number of positive charge has to be equal to the number of negative charge. So we have ion 3 plus like that, and SO4 2 minus. What do we need to make the charges equal? Here there's 3, here there's 2. So to make the charges equal, we can use 6. So we can add one more ion there, ion 3 plus, so that the net charge should be +6. And we can add 2 more of these, like so, so that the net charge should be -6. Therefore, for these two, for iron and sulfate, to form an ionic compound that has balanced charges, we're going to need two ions. So Fe2, so we have got 2 ions, and 3 sulfates, 1, 2, 3. So to show that there are 3 sulfates, we say SO4 because it's a radical. They are sulfate. So I just can't write SO4. I can't write it like this, SO4 3. I have to put brackets to show that there are 3 of these, 1, 2, 3, so that the charge should balance. So next time when you're trying to write the formula of an ionic compound and you realize that, okay, this is Fe3 plus, and this is SO4 2 minus, and then you cross multiply, you end up with this, it's correct, but you have to work out the reasoning in your head. The reason why I'm cross multiplying is for me to have the number of positive charges should be equal to the number of negative charges. Make sure again you watch this video once more so that you should have a better understanding of this topic. So me teaching you this, it's going to make it easier once we start doing ionic structure and chemical bonding, atomic structure and chemical bonding. Actually, when we start doing chemical bonding, we're doing atomic structure today, and there are slides towards the end. But once we start doing the details, once you start knowing, all right, so that's the valency, that's the electronic configuration, and then these electrons go to nonmetals, you're going to be able to see things properly, and things are going to be able to make sense. So let's now look at naming acids. So there's a topic called acids, bases, and salts, but it's a good thing to understand how we name acids in this introductory lecture of chemistry. So that once we do acids, bases, and salts, properties of acids, properties of bases, reactions of acids, reactions of bases, and how to prepare salt crystals, a question can come, define an experiment, how you can prepare potassium sulfate crystals. So you have to know the definition of acids, and you also have to know how to name acids. So by definition, an acid is a proton donor. An acid is a proton donor. So what it means here is that it donates protons. And please, as when it comes to acids, this word here, proton, does not mean what's in the nucleus of an atom. This word proton, when we're talking about acids, we mean the hydrogen plus ion. So when we say a proton here, we mean it's a hydrogen plus ion. No wonder the other definition of an acid is any substance which, when dissolved in water, produces hydrogen plus ions as the only positively charged ions. So here, when this dissolves in water, for example, if we have a chloride ion, and this is water, H2O, this chloride ion, once it dissolves in water, it's going to produce hydrochloric acid without the charge. So it's going to produce hydrochloric acid. And because this hydrochloric acid, this H there, it has got this H plus ion there. So hydrochloric acid, H plus Cl minus. If we dissolve this in water, we're going to make hydrochloric acid. So because of this thing here, this is known as the proton, which makes it an acid. So once this hydrogen and this chloride dissolve in water, we're going to make a hydrochloric acid. And since water, you know, water partially ionizes things, water actually ionizes things. So this solution is going to contain these hydrogen plus ions. So two definitions. An acid is a proton donor. I'm going to explain what I mean when I say an acid is a proton donor, when you have things like what hydrochloric acid plus maybe sodium hydroxide to give you sodium chloride plus hydrogen gas. So we're going to look at things like that, where we are going to see that, okay, this hydrochloric acid has donated this proton. No wonder I said always think about protons as hydrogen plus ions. So this hydrochloric acid is going to donate a proton to this sodium hydroxide to produce a salt and water. So H2O, to produce a salt and water. In the future, we're going to know that this is called a neutralization reaction, that every acid can react with a base to produce a salt and water. And in the process of producing this salt and water, the acid is going to donate a proton. So by proton, again, in acids, bases, and salts, we consider protons as hydrogen plus ions. So this proton here, this hydrogen plus ion, will be donated to this base, sodium hydroxide, to produce this salt, sodium chloride plus water. So in this sense, an acid is a proton donor, but in this sense, when it dissolves in water, it's going to produce hydroxide ions as the only positively charged ion. So how do we name these acids? If you were to ask a question, how do we name these acids? This is a nice topic. You're going to learn what a strong acid is, what a weak acid is. It's a very interesting topic, and it's rather simple. And questions always come again on acids, bases, and salts. It's one of the big topics in chemistry. So how do we name acids? So we name acids according to the anion that we have. And remember, anions are nonmetals. They are nonmetals that gained electrons. So they are nonmetals that gained electrons. If you gain electrons, remember an electron is negatively charged. So if you are gaining something that's negatively charged, you're going to become more negative. You're going to become an anion. So for example, chlorine, I think it has an electronic configuration of 287. We're going to talk about this. So chlorine, once it gains one electron, for it to have a complete electronic structure, it's going to go from chlorine element to a chlorine anion, which will be called chloride, which will have an electronic configuration of 288. So these are what we call anions. They are always nonmetals that gained electrons. So if your anion ends with IDE, the acid name will be called hydroic acid. So if the anion ends with IDE, the acid will end in ic acid. A good example of an anion that ends in IDE is this one, right? Chloride. Chloride ends in IDE. So if chloride dissolves in water, the acid that will be formed will be hydrochloric acid. You've seen that, hydrochloric acid. Hydrochloric acid. Let's look at, let's say, another anion, let's say sulfur. If sulfur gains an electron as an element, it will be called sulfide. It will be called sulfide, S2 negative. So if sulfur gets dissolved in water, we're going to form something known as, let me write it, let me draw this, so that you see it properly, so that I also go about telling you again how to name binary ionic compounds. So let's say sulfur has dissolved, let's say sulfur has gone from an element, sulfur, so we have got sulfur there as an element. So this is sulfur, the element, denoted as S, very unstable. So to become stable, it gained a few electrons and became the anion. It became the anion sulfide. Sulfide, IDE, S2 negative. You're going to see what these two negative comes from something called valency. So if you look at the electronic configuration for sulfur, you realize that, all right, it will need 2 electrons for it to have 8 electrons in its outermost shell. Let me just write this charge closer to the sulfur, like so. So this sulfur here, once it dissolves in water, water contains hydrogen ions. So once it dissolves in water, hydrogen has H plus there, and sulfur is H2 minus. You can cross multiply there to make a substance known as H2S, which is sulfuric acid. Or again, why are we cross multiplying? We want the positive charge to be equal to the negative charge. So since it's like that, we'll just need one more hydrogen there, so that we should have two hydrogens and one sulfur, so that +2 there should be equal to -2. So because sulfur has dissolved in water and it's become a sulfide, it's become an anion, it's gained electrons to become a sulfide. Because it ends in IDE, the acid that it's going to be called, once it dissolves in water, will end in ike. So H2S is called sulfuric acid. It's called sulfuric acid. Are you following?
Yes.
Hello, Fabi, are you following?
Yes.
Fabi.
Yes.
All right, I know I'm saying a lot of things, but things are going to make sense once you get the lecture video. So remember, to name an acid, we look at the anion. So the anion is going to determine what type of acid it's going to be called. So let's take, for example, again, a polyatomic anion. Those radicals that I told you to memorize, one polyatomic anion was, let's say, sulfate. Let's say sulfate. So the anion is now a radical. So let's take a radical called sulfate, SO4 2 negative. Let me spell it out. Sulfate. So sulfate ends with ATE. So what's the rule? If the anion ends with ATE, the acid will end in ike. So the acid will end in ike. So sulfate, let me show you this table. Where are we? Okay, sulfuric acid because of the ATE. Sulfur, sulfide, so sulfuric acid. Oh, okay, it's okay, it's the same thing. So the other sulfuric acid. Mhm. Oh, all right, so I just made one slide error. On this one, I was explaining on sulfuric acid. Oh yeah, I knew something was off here. Sulfuric acid comes from this radical, the sulfate. So a good example of this one is the hydrochloric acid that I explained. So IDE, chlorine, chloride, IDE, hydrochloric acid. But sulfuric acid comes from this radical. Yeah, that's where I made a slight error. So hydrochloric acid. So let's take, for example, of a radical, for example, sulfate. So sulfate ends with ATE like that, meaning once this sulfate dissolves in water, the acid is going to end in ike also, just like when the anion ends with IDE. So sulfate, again, the charge is 2 negative. For these, the radicals, you have to memorize them. If you remember, that's the radical table, it was written polyatomic anions. So the charge here is 2 negative. So it will be the same thing, but I messed up the S. So hydrogen, H plus, again, you can cross multiply so that the formula should be H2SO4, or you can tell yourself that, okay, I have got one hydrogen this side, I have got two sulfates this side. I have got a 2 minus charge and a plus 1 charge. For them to be equal, I'm going to need one hydrogen charge so that we can have two positive that side and two negative. So the formula will be H2SO4, which will be sulfuric acid. Yeah, sulfuric acid. Why is it ending in Ike? Because the anion was ending in 8. So sulfuric acid. What of a scenario where the acid ends with, where the anion ends with IT? Where's my cursor? Okay, there it is. So where the anion ends in ITE, what example can we give of an anion ending with ITE? So there's an anion known as nitrite. We have an anion known as nitrite. From the polyatomic ion table that you have to memorize, I highlighted a few things in the chemistry video of things that you have to memorize. So I've got nitrite, like so, and nitrite should be NO3 negative. I'm not so sure, but I think it's NO3 negative. Yeah, it should be NO3 negative. Let me just make sure. Nitrite, these things are a little bit confusing. I usually forget. So nitrate NO3 2 negative. Nitrite ion is NO2 negative. Okay, I knew the charge was a minus, but not the number of oxygen ions. So it's NO2 negative. So nitrite is NO2 negative because nitrite ends with ITE. Once it dissolves in water, so hydrogen plus and NO2 minus, this one, the charges are already balanced, one positive there, one negative. But because it ends in ITE, when it dissolves in water, the acid that will be formed, NO2 negative, will be called nitrous acid. It will be called nitrous acid. So that's how you name acids. How do we name acids? We look at the anion. If the anion ends with IDE, for example, chloride ends with IDE, the acid will be called HCl, hydrochloric acid. If the anion ends with ITE, like nitrite, the acid will be called nitrous acid. Again, another scenario, if an acid, if the anion ends with "-ate", for example, sulfate, SO4 2 negative, the acid will be called, will end in "-ike", so sulfuric acid, just like that. So that's how you name acids. That's where all acid names just come from anions that have been dissolved in water. So the acids that I want you to know by chemical formula, actually, I want you to draw this table. So in your chemistry book, make sure you draw all these diagrams. So draw this table and you can memorize it so that you know how to name acids. Because at times, no one at grade 12 level, maybe in grade 9 they usually write chemical formulas for students, and all you have to do is just tell the examiner what type of reaction it is. Is this a displacement reaction? Is this metal dissolving in water to produce a metal oxide? They'll write everything, all the information will be given. But in high school, you have to balance the equation on your own. You have to know how to write the chemical formula on your own. You have to know how to even calculate more ratios from the, especially when we go to the more concepts, you have to write the equation, you have to balance the equation. After balancing the equation, you have to use more ratios and formulas like Avogadro's number and other formulas for more concepts to sort of do some calculations. So if you don't know how to write formulas, things are going to be very hard for you. So at least make sure know all these acids, at least the common ones: hydrochloric acid, sulfuric acid, this weak acid, carbonic acetic acid, oh, not carbonic acid, acetic acid. Know all these, actually know everything, with the top three being hydrochloric acid, sulfuric acid, and acetic acid. Why am I saying acetic acid? Because the question can say, give an example of a weak acid. Acetic acid is a very weak acid because uh, it comes from this alcohol, COOH, OH, because it's an alcohol. We're going to look at organic chemistry or organic compounds that end in OH as their alcohols. Or, oh no, it's a COOH, it's a carboxylic acid. Yeah, it's a carboxylic acid. Because of this H here, you discover that acetic acid only has one hydrogen to give. And once it gives off this acid, that's it. It cannot take part in another reaction with a base. So no wonder they say it's a weak acid, because all of its hydrogen ions can be taken away just with one reaction with a base. So no wonder I said no acetic acid. Then sulfuric acid and hydrochloric acid. Sulfuric acid is an example of a strong acid because it has got two hydrogen ions there. So you have to know these three at least. This one, hydrochloric acid, it comes very common in terms of acid-base reactions and preparation of salts. So you have to know these acids. But just remember, draw the table. You draw the anion name in words, the acid that's been formed, and the acid word in words also, so that you practice. Okay, so now let's talk about atoms. What is an atom? What's inside the nucleus of an atom? So last time we talked about elements, and we did say that elements are substances in their purest forms that cannot be split by physical or chemical means. So why can't elements be split by physical or chemical means? Because they are made up of atoms. So this right here is an atom. And remember, like I said, atoms have no charge. What do we mean by atoms have no charge? They are electronically neutral. But again, just because they have no charge doesn't mean they are stable. Atoms are very, very unstable. No wonder they form bonds with no wonder elements form bonds with other elements to form compounds so that they gain stability. When they say atoms have no charge, it means they are electronically neutral. It means the number of electrons should be equal to the number of protons that are positively charged. So this charge balance makes an atom electronically neutral. So an atom has got three subatomic particles. We call them subatomic particles. Three subatomic particles. We call them subatomic because they are the building blocks of an atom. So an atom is going to have a nucleus, as you can see. So the nucleus from this diagram here, let's start from the inside going outside. So an atom is going to have a nucleus, and this nucleus here is going to have two fundamental subatomic particles. This nucleus is going to have protons. The protons carry a charge of +2, and the neutrons carry zero charge. These don't have a charge. They are just there to stabilize the nucleus. And remember, the number of protons is extremely important because it's also called the atomic number. The atomic number is the number of protons. It's the atomic number that assigns element names on the periodic table. So if this is helium, let's say 2, helium 2, 1, this is the number of protons. A helium atom or any element of helium is going to have 2 protons in its nucleus. So number of protons, extremely, extremely important. So what do you have to know about the nucleus? It consists of protons and neutrons. Protons are positively charged. Neutrons have no charge. Protons have a mass number of have a mass of 1, and neutrons also have a mass of 1. So these two sort of balance each other, but the protons have a positive charge and the neutrons have no charge at all. Then outside, we have got things known as electrons. Electrons in an atom, they are found in energy levels known as electronic shells. So these are the electrons in the outermost shell electron. So let me tell you an interesting fact about electrons. Two interesting facts about electrons which relates to their small size. So have you been to a stadium before, or have you seen a stadium before?
Entonces, mpira kwenye redi kama gani?
Hello, Fabi. Have you seen a stadium before?
Yes.
So a stadium would be sort of like this, a huge pitch or a huge field. So if you get a small marble, those marbles that kids like to play around with, if you get a small marble and you place it around the stadium like that, this small marble in your stadium will symbolize your nucleus of the atom. And then the first seat, very far away, the first seat, that's where you might find maybe one electron. And then another far away seat, you might find another electron. Maybe another far away seat, you might find another electron. So that's how far away electrons are. The nucleus is the biggest portion, and everything else is empty space. So that's the distance between the nucleus, a very small compared to the entire space of an atom. The nucleus of an atom is just at the center, very small, then everything else is entirely empty space. Everything else entirely is literally empty space. And you might find an electron very far away and it's very small. The second interesting fact about electrons are so small that no one on this planet has ever seen an electron scientifically. We know that electrons are there because we can measure their charge. We know that electrons are negatively charged. We can also measure their spin. We know how they spin around the nucleus, like they spin like the way the planets orbit the sun. And we also know their effects. Okay, we know that, all right, when something gains electrons, it's going to become an anion. Electrons take part in various redox reactions. So we know the effects of electrons. But electrons are so, so small that no one has actually seen an electron. They are like 0.0000000 something mass. They are so small. So usually, where's that card table? Anyway, there's a card table that I wanted to show you. It usually comes like this. They will say subatomic particle. Then they will say charge. Then they will say mass. Then they might say location. Then they will say protons, neutrons, electrons. Then they'll say complete the table. They'll say complete the table. You know, examiners don't want people to fail. They just want to know whether students have understood the concepts. So in paper 2, they'll start bringing atomic structure, very simple questions, and they'll even say, complete the table, 5 marks. Then you say, okay, protons, the charge is 1, they carry a positive charge, and the mass is 1, and they are located in the nucleus. Then you say, okay, neutrons, they have no charge, it's 0, they have a mass 1, and they are located in the nucleus. Then you say, all right, electrons, they have got a negative charge, and their mass is so small, it's 0.00018 something. Sometimes it's represented as a very big fraction with a very huge denominator to show that there are a lot of zeros. It's the mass of an electron is almost 0. If you round off the mass of an electron, you'll find that it's 0. So it's very small. You can either put it as a fraction. I'll find the exact number. I'll find this table for you, and I'll send it to you. Then the location, you say, all right, electronic shells. Electronic shells. So because protons and neutrons are found inside the nucleus, at times the number of protons and neutrons will be called the nucleoid number.
Auntie, mommy, on my umbrella. Okay, next.
All right, so let me repeat that again. Let me actually write it down here.
Thank you, mommy.
So because protons and neutrons, because these two subatomic particles, they are found in the nucleus. So the number of protons and neutrons in an atom is sometimes called the nucleoid number. So don't become confused when you hear nucleoid number in an exam. Nucleoid number comes from the word nucleus. So what's in the nucleus? Protons and neutrons. So because these are found in the nucleus, they are going to refer to this as the nucleoid number. So if you see nucleoid number, it denotes the number of protons and neutrons found within the nucleus of an atom. All right. So what we learn about how electrons are arranged in an atom comes from this scientist known as Bohr. So in grade 12, we learn the Bohr's model of an atom, but when you talk about A-level chemistry, you start talking about Planck's quantum mechanical model of an atom, which doesn't matter in grade 12. But the way an atom looks like to you is that it consists of a nucleus, and the first energy level is going to occupy only 2 electrons. The second energy level occupies 8 electrons, then the third 8 electrons, just like that. So your electronic configuration in high school goes like 2, 8, 8, 8. So an atom wants to have either an octet or what do you call 2 electrons? Did I write it down here? The noble gases only have 2 electrons in their outermost shell, so they are called an octet. But what do you call 2 electrons in the outermost shell? All right, I didn't include this in the notes. So again, this is just what I was explaining. You can write these notes, but the explanation that I want you to know is that the Bohr's model states that atoms have a nucleus surrounded by electronic shells. And the first shell can only be occupied by 2 electrons. The second, third, fourth, etc. shells can only be occupied by 8 electrons in their outermost shell. This information is enough for you to pass an exam in high school. So the Bose model, we're not going to talk about weird quantum mechanical models of an atom. So I want to introduce the concept of valency. Where are we? Isn't it here? So octet is 8, 2 electrons. Okay. Yeah, sure. All right. So I want to introduce the concept of valency here. So valency. So valency is actually the bonding power of an element. So for example, like I said, we have got things like sodium and chlorine. Sodium is going to have an electronic configuration of 8, 281. Then chlorine is going to have an electronic configuration of 287. So the valency of sodium will be 1, and the valency of chlorine is also going to be 1. Remember I said there's a difference between valency and valence electrons. Let me say that, let me show you the difference. So the valence electrons, so here sodium and chlorine all have 3 electronic shells. Sodium has got 1 electron in its outermost shell, meaning the valence electrons. So you see the difference. Valence electrons are electrons in the outermost shell. So valence electrons for sodium, it's 1. So sodium, how many valence electrons does sodium have in its outermost shell? 1. So valence electrons for sodium, 1. How many valence electrons does chlorine have in its outermost shell? 7. So those are valence electrons. Valence electrons are electrons that are found in the outermost shell, the last shell of an element. But this word here, valency, means bonding power. How many bonds, how the strength of bonding the element has, like how many electrons does it need to have a complete outermost shell electron. So that's the term valency there. And valency can be shown by the position of an element on the periodic table. I'm going to show you how you can determine the valency based on the position. You know that, all right? So this atom, this element actually just needs 1 electron, so it's going to have a valency of 2. So here, it's going to have a valency of 2, a valency of 1, based on its location on the periodic table. So the valency of sodium and chlorine, they are actually the same, because here sodium has to lose 1 electron, so it has got a valency of 1. So valency of 1, because it just has to lose this one. But chlorine has to gain 1 electron, so it also has a valency of 1. So valency is the number of electron that an element has to lose or gain for it to have a stable electronic structure. What's a stable electronic structure? This here, the octet configuration. You need 8 electrons or 2 electrons in your outermost shell. The only elements that have 2 electrons in their outermost shell are your noble gases, those that are perfect, literally electronically neutral, like helium or helium, xenon, helium and xenon. If you look at your last period, your last group on the periodic table, you're going to see noble gases that only have 2 electrons in their outermost shell. But standard, you need 8 electrons. All elements, except from noble gases, need 8 electrons in their outermost shell. So the number of electrons that they need for them to have a complete outermost shell electron is called the valency. So these two here, they have the same valency. They both need 1 to get rid of one electron or gain one electron for them to have a complete outermost shell electron. So please, from today, there's a difference between valency and valence electrons. Let me say it again. Valence electrons are just the electrons that are found in the outermost shell of an element, while the valency is the bonding power. The bonding power. By bonding power, we mean how many electrons does that element need to lose or gain for it to have a complete outermost shell electronic configuration. Are we together?
Yes.
All right, so let's get to, oh my, it's 14. I hope this is the last, I think this should be the last part. So coming to this again, I remember explaining this on the periodic table. For any element X, you are going to find a big number. It depends the type of periodic table. Sometimes they interchange, but the big number on top is the mass number, which can also be called, remember, the nucleoid number, which denotes the number of protons plus neutrons found within the nucleus. And then the number below there is the atomic number, or proton number. So the atomic number is the number of protons that are found within the atom. And this number of protons, the number of protons has to be equal to the number of electrons. So we can determine the number of electrons also by looking at the atomic number. So please, the number at the bottom, it's not the number of electrons. It's not the number of electrons. The atomic number is the number of protons that are found within the nucleus. And the number of protons, we can have some form of idea as to how many electrons an atom has, because an atom is electronically neutral. The number of protons has to be equal to the number of electrons. So please, this number here at the bottom, it's not equal to the number of electrons. It's the atomic number, which denotes the number of protons. And don't forget its significance. The atomic number tells you that this is a helium, this is an element of helium, this is an element of carbon, this is an element of nitrogen, this is an element of chlorine. So all elements have their own unique, atomic number. It's like a fingerprint. You know, your fingerprint is unique towards you. No wonder you go to your voter's registration, or when getting an NRC, they get your fingerprint. It's the same thing as the number of protons, or the atomic number. So remember, the atomic number or the proton number is a unique number to all elements, extremely unique. It's the one that dictates this is a hydrogen, an element of hydrogen, an element of nitrogen, an element of chlorine. Very, very unique number. Oh, here's the table I was talking about. Do you see how huge this denominator is in terms of an electron? 1 over 1,840, 1840 will give you 0.00000 something, showing that an electron is very small. No wonder I said no one has ever seen an electron scientifically. We can only determine the charge of the electron, the spin, and its effects, the effect that it has on a given element. All the reactions, all the chemical reactions that we see in nature are as a result of electrons jumping around, forming anions and cations, but they are very small, invisible. No one, not even using the most powerful, sensitive microscopes, atom smashers, no one has ever seen an electron. This denominator is very big. The denominator is very, very big. So this table carries 5 marks in the exam. Usually in paper 2, you're going to find this table. It's very common. It always comes 5 marks. What is the charge of a proton? So know this table, draw it in your book. You can stick it somewhere, just you can memorize it, but just know this table. 5 marks towards your exam. Okay. So this is just an example of what I was saying. So nitrogen, an element of nitrogen, on the periodic table, it appears like so. So this big number there is the mass number or the nucleoid number, which tells you the number of protons and neutrons that an element of nitrogen has. Then this small number here is your proton number or your atomic number, which tells you the number of protons. And always remember, your number of protons will be equal to your number of electrons because an atom is electronically neutral. All right, so this is the last part because the rest they are just questions. Aqueous hydrogen reacts with use aqueous sodium chloride and what's this? Okay, we're going to do these questions in the next. So can we do these questions? Give the medical drove. We'll do these questions next time. They'll require me to explain for like 80 minutes again. So isotopes, So in any language, in any scientific language, when you see iso, this word iso means same or identical. So isotopes mean same or identical. So what is common about isotopes? What is the same about isotopes? That's the first thing that you should understand. Iso means same. So what is the same or what is identical about all these elements? Remember the unique number, the fingerprint. What's the unique number? The atomic number, right?
Yes.
So the atomic number is the iso part. So the iso means atomic number. So if you want to remember this, the word atomic here has an O, right? And the word iso here has an O. And you are going to understand that iso means the same. So you're going to be like, okay, so maybe a question says define an isotope. You see this O there, you're like, okay, atomic number. Then you see, okay, this same here, iso, you see this iso. First you see iso, you say, okay, iso means the same. Then you see this O on iso, you'll be like, okay, the O is equivalent to atomic because atomic has a 0. So you're going to say, okay, isotopes, you start your definition, you say isotopes are atoms, they are atoms of the same should always be there because iso means same. They are atoms of the same element. Then you're going to say, what do they have in common? Having the same, because now you know the same is atomic, so you say having the same atomic number.
That's
Yes. Different.
but
Yes.
mass number.
Exactly, yeah, mass number. So mass number is what's found inside the nucleus. So what's found inside the nucleus is the mass number, the number of protons and neutrons is the mass number. Again, mass number can also be called nucleoid number. So having the same mass number, open brackets, I'm just putting this for you because examiners can confuse you, nucleoid number. So same mass number, or nucleoid number makes an isotope. So you can see here, we have got two types of isotopes. Even all elements have got isotopes. No wonder a standard periodic table, the periodic table that we tend to use at A level, the mass numbers or the nucleoid numbers usually have decimal points to signify the existence of different types of isotopes. But your periodic table, they just round off. So you can see here, first of all, we have got different types of isotopes of hydrogen. Different types of isotopes of hydrogen. The first thing that you have to identify is the atomic number is always the same, because that's the uniqueness, that's the fingerprint. So an atomic number of 1 tells us that this is an element of hydrogen. An atomic number of 6 tells us that this is an element of carbon. An atomic number of 17 tells us that this is an atom of chlorine. But what will be different will be the size of their nucleus. Some are going to have more neutrons. Most of them are going to have more neutrons, increasing the atomic number by slightly a bit, maybe by 1 or 2. So here, hydrogen, we've got deuterium, and we have got hydrogen, which is 1, deuterium with 2, and tritium, which is 3. Isotopes of carbon, we usually name them as C12 or C14. So some will say carbon 14, carbon 12. Same with chlorine, chlorine 35, chlorine 37. But most of all, the examiner just wants you to know how to define an isotope and maybe give examples of certain elements that have isotopes. And you can say, okay, hydrogen, you can say deuterium and tritium. But how do you know? Iso means same. What is the same? You look at this O here, the O rhymes with atomic number because atomic has O. So you're going to say isotopes, they are atoms of the same element. What do they have in common? They have the same what? Atomic number, right?
Atom.
Excellent. But what's different?
Mass number.
Which is also called what? The nucleoid number. So the mass number is also called the nucleoid number. All right, so I'm going to end here. The next time we do chemistry, we're going to do some questions so that we solidify these concepts. Okay, I need to rush to my meeting with my research supervisor. So let me just send you the lecture video before I go out because I might forget. All right, I'll see you next week. I have a test on Tuesday, so throughout Saturday and Sunday, I'll be in the library studying. All right, see you on Monday for civic education. All right, bye.